Yes, good morning, Roger. Hello, Helen. And
Hello, hi. Can you hear us okay?
yes, we can.
Excellent. And we're just sharing the screen now. So hopefully, can you see Roger's presentation now?
Yes, and it's on the timing of conscious experience and consciously controlled actions.
That's right.
Okay.
There we go.
Right.
Yes, Roger, please come in. Thank you.
Yeah. Okay, well, thanks for the opportunity. And I hope that what I say can be expressed adequately in the time available. Basically, what I want to say, as far as I'm concerned, dates back to experiments that were performed by Benjamin Libet towards the end of the previous century. And I won't start by talking about his experiments, but they do seem to indicate something strange about the relationship between, the timing of conscious experience, because it seemed to indicate that there was something of a delay between the actual thing that we're experiencing and the experience that we have. This also ties in with various problems that people have these days about trying to explain how rapid actions can happen. When you have something like a tennis player or a ping pong player, I used to play ping pong when I was at school, and I quite appreciate that if you want to make a decision at the last minute whether to hit the ball one way or the other, you have much less than half a second to do this. Whereas, according to current neurophysiology ideas, this would be all done unconsciously. But yet I had the distinct feeling that I was deciding which way to hit the ball, that it wasn't just completely unconsciously controlled. So these issues seem to be puzzling. And the Libet experiments are also puzzling, but in a related way, which I'll come to. I won't mention the experiment immediately because there's something Stuart tells me is not quite correct about what I say. It's not importantly not correct, but I'll come to that later. First of all, I want to talk about the Orch-OR program and the kind of physics that's involved in it, and why there could be strange things about timing involved in that. So let me move forwards. Which way do I move in this one? It's the middle one. Okay, thank you. I want to talk about how the quantum state, see that the Orch-OR proposal suggests that there is something deeply quantum mechanical, but not just quantum mechanics that's involved. It's how quantum mechanics needs to be in some sense completed or corrected by incorporating, well, you see, I mentioned here the two processes by which a quantum state evolves. The first thing is the Schrödinger equation, which tells you how the wave function evolves with time. And it's a perfectly deterministic equation, and it's easy to write down, although to use it can be very complicated. But nevertheless, it's a deterministic evolution. But then this doesn't give you what you need to know about it, the result of a quantum object, how it behaves, because at a certain point, the quantum evolution, according to the Schrödinger equation, seems to be departed from. This is more or less what's said when you make a measurement on a system or something, or you wheel out of the cupboard some device which magnifies the quantum state into something more macroscopic. And at that time, it becomes a probability mixture of different alternatives, which is not what Schrödinger equation tells you would happen. It's something else. It's something called the Born rule, which you have to add to the Schrödinger equation. In fact, it's inconsistent with it in a sense, because the Schrödinger equation is a deterministic equation, whereas the collapse of the wave function, according to the Born rule, it converts this quantum state into a probability mixture of alternatives. Now, to say a little bit more about quantum mechanics at its basic level, you have a thing called the quantum superposition principle. And this is that if A is a quantum state and B is a quantum state, then you can construct a whole slew of other quantum states by taking a multiple of A plus a multiple of B. But these multiples are complex numbers. So the A and the B, the alpha and the beta, which are the coefficients here, are complex numbers. They could be either real or complex. And the probability when you change to the other proposal for what happens in quantum mechanics, you have to say that there are either one or the other, not the superposition of A and B, is either one or the other, with probabilities given by the squared modulus of the numbers alpha and beta. I want to give you a feeling for the fact that these quantum amplitudes, those are the alphas and the betas, those are the complex multipliers that you apply to your state. I've written them as W and Z in this picture here. Doesn't matter, they're the same things. And what's rather nice, I've always liked this example, because you can see the interplay between these complex numbers, and they have to be complex numbers, they can't just be real numbers, because of this very simple situation. This is quantum spin for a spin half particle, so it could be a proton or something, and the spin direction, it always rotates, it always has a spin of a half h cross, it's a definite amount, but the direction of the spin can be any direction in space, but it's dependent upon two directions. So you could take your basis states as up and down, and then you can work out the state angled in the picture 45 degrees out to the right. And it's a sum of multiples of those other two, and this could be a complex combination, because the multiples could be a whole sphere's worth of combinations, and you can't get that with just real numbers. So it's an amazing way in which you can see this basic role for the complex numbers in quantum mechanics, which involve the square root of -1. That's what I mean by complex number. These complex numbers are crucial to the way that quantum mechanics behaves and relates to our experiences in ordinary three-dimensional space. Okay, let's move on here. That's the basic principle of quantum mechanics, is the superposition principle. If you've got two quantum states, you can always produce a third, or it could be several complex quantum states, which you can combine them together in all these ways. That's the basic principle of quantum mechanics. The basic principle of, I'm going the wrong way, of general relativity now is the principle of equivalence. Here, top picture, I'm imagining what Galileo would state is if you dropped a big rock and a little rock from the Leaning Tower of Pisa, then as they fall, and he knew about air resistance, he knew that if you dropped a feather and a rock, they wouldn't fall together, but that was because of air resistance. He was well aware of that fact. But if you had something you could remove, if you could ignore the air resistance, which would be the case for nice massive objects, and then you can, if they drop, they will drop together. So a little insect sitting on one of the rocks looking at the other one, it will seem as though gravity has been cancelled out momentarily. As you fall freely with gravity, gravity is in some sense cancelled out. In the bottom, we have a more modern version, where it's more 2001 space station there, not like the actual space station. Never mind about that. And here we have an astronaut, and the astronaut is floating freely, despite the fact that the Earth is right there and its gravitational field should be felt by the astronaut, since the astronaut is falling freely in the gravitational field. And falling can be in orbit, doesn't have to be falling downwards. Falling freely in the gravitational field of the Earth cancels out the field, and that is the principle of equivalence, is that locally you can cancel out the gravitational field. Now, the point about these two things, sorry, I'll have to go back because I might have mastered how to make this thing work. Okay. I'm claiming that there is a lifetime for a superposition like this. The formula for the lifetime was actually produced by Dioschi. I wasn't aware of his work on this before I found it myself. He was about 2 years ahead of me, I think. But I had a reason for believing this formula, which was, I don't know quite what his reason was, but I'm not sure I've got my slides in the right order here. Let me just check to see whether that's correct. Yes, that's correct. Okay. The length of time, you see, suppose you have a body which is put into two locations at once by quantum superposition. Then, according to ordinary quantum mechanics, there's no limit to this. You could put great big lumps in superposition of two spots. And according to standard quantum mechanics, you could have all these amplitudes of different possibilities and they would just stay there. Doesn't make any sense in reality. And the idea is that you have a lifetime for that superposition, and it will become one or the other in a lifetime, which is what's called EG or E sub G. And this quantity, e.g., the reciprocal of it, it's actually, I can explain what it is. If you take the lump in, suppose you have an object to be put into a superposition of two places. You imagine that you have two instances of the object on top of each other. So the object could be two of them right on top of each other. And then I'm going to move one of those instances away from the other. And I'm considering the forces which pull it together, which I ignore all the forces which are important in ordinary physics and go on. Nuclear forces, chemical forces, all those things I'm completely ignoring. All I'm considering is the effect of gravity. There is a certain gravitational pull on one of these lumps on the other. And as I pull these two lumps, this lump and its partner, to a certain distance away from each other, then this quantity, e.g., is the amount of energy pulling one away from the other would cost me to do this, considering only gravity. So for an ordinary, really, really tiny, the nuclear and quantum effects would be enormously larger. So you would normally see this effect. But if you could subtract all the other effects out, this effect of the gravitational pull, you're pulling against the attraction of one version of the lump against the other version of the lump, and that gives you the value of Eg. And the reciprocal of Eg, or H cross over Eg, is the half-life, if you like. It's like a decay of a quantum nucleus or something. The decay time is the half-life, is essentially H cross over Eg. Okay, now this is giving you, I now want to talk about quantum reality. Albert Einstein produced a notion of reality. And this Einstein's notion of reality, the question he was really addressing, is the quantum superposition real in any sense? Is the Schrödinger equation describing the evolution of a real thing? What is this thing that it describes which is real? And Einstein was introducing an idea of the kind of reality which I'm going to call quantum reality. He didn't call it that, but the kind of reality he was concerned with was that if you can perform an experiment on your state for which, without disturbing the system, you can get a well-defined answer, then that gives you an element of reality to this answer. And this is what I'm calling quantum reality. You have to know what you're trying to measure. This is the thing. And if you go back to the example I had before, well, I think I have to go forwards, I think. Yeah, here we go. This example, you see, this is really giving a quantum reality to all these possible different rotations of the spin state. You see, you could have a system in which this particle, you say, well, I know by what the calculation I've done, which way it ought to be spinning. It ought to be in the direction pointing outwards to the right. I've indicated with the letter U. That direction is the state of this particle. Now, quantum reality, you can check whether this is right or not. You can perform an experiment to measure if the spin is in that direction. And it doesn't disturb the system if you've got it right. And it gives it the right answer. If you've got it right, it will say, yep, you've got it right, 100%. That is to say, you try this experiment many, many times. Each time, the answer says, yep, you got it right. If you got it a little bit wrong, maybe then 80% it will say you got it right, and 20% you will say you get it wrong. It also disturbs the system too, because the next time it will be flipped into the way, either the direction you've measured it or the opposite direction. So the quantum reality can be disturbed by a measurement like this. And the point about it is you can't ask the system which way you're spinning. You can't say, particle, what's the direction of spin? It looks at you blankly. It doesn't give you an answer. However, you've got a good idea as to which direction should be spinning by now. You've done your calculations, so by now it should be out 45 degrees to the right. And then you perform your experiment, 100% absolutely gives you the answer. So that is the Einstein notion of reality, and that is quantum reality. See, classical reality has a different kind of ontology. The quantum reality of a state might be something I'm calling X here, and you can ask your system, what is your spin, or what is your state? And if it's if it's classical reality, then it can say, yep, my state is X, and it's got this structure, and it's sort of curved top and bell shape at the bottom or something like that. It can describe itself in detail. And that is classical reality like that. It's much more kind of robust kind of reality. But quantum reality is not like that. It looks at you blankly. If you ask it what state it is, you can have a go at suggesting what its state is. You can say, is your state by any chance X? And if you have it right, 100% of the time, it will say, yep, its state is X. So you see, it is a kind of reality. It's a firm kind of reality. It's a good idea of a kind of reality. But the idea is to realize that it's not the same, that quantum reality is different. Now, there's another thing about quantum reality, which I'm indicating in this picture. I'm imagining, this is a space-time picture. Time is going up the picture, and I'm imagining you have a body indicated by the thick vertical line at the bottom, which is split into a superposition of two alternative paths. That's the dotted lines as you go up. And then, because of this criterion, it becomes one or the other after a certain time, after this EG over 1 over EG time, H bar of EG time. And at that time, it will become one or the other. Roughly speaking, it may be earlier, it may be later, but on average, it will be that time. And then it becomes either location Q or location Q star. Now, if this is a relativistic picture, there's a little bit of a problem, because in relativity theorem, in theory, you have to consider the S surfaces. These are meant to be three-dimensional surfaces. I can't draw them all in this dimension. The S surfaces are an observer moving rapidly over to the left, and according to the simultaneity of that particular observer, that observer would consider that the Q thing had disappeared. No, it was still there before the Q had disappeared. So it's still there with a small probability of existing, and Q star has a small probability of disappearing. But nevertheless, if you cut it the other way, then, well, if you cut it this way, they're both there for a while, even though Q is supposed to have disappeared. Let's think of the observer going the other way. It's even worse there. The observer going off to the right, and they're tilted the other way. T naught and T, well, both of them agree for the right beginning state. But later on, according to the T observer, there's a good chance that Q will have disappeared while Q star is still in the superposition. You see the line hits the probability line, but it's still in the superposition. So it might disappear too. It might be a small probability, but it could disappear too. That's nonsense. They can't both disappear. So this picture doesn't make sense. That's what I'm trying to say. How do you make this picture make sense in relativity? The story is a little bit more complicated than that, but I won't worry about this because the simple answer is what I consider to be the correct answer. The simple answer is that the bifurcation actually takes place as though it had done right at the beginning. So even though the decay time, it becomes one or the other in a certain length of time, it tracks itself back to the origin point, and then it becomes as though Q star was the truth all the time. So classical reality is in fact following what actually the reduction says happened, but it happened as though it had happened right at the start, not later on. It looks like a paradox. I don't think it is a paradox. In fact, it's quite strange. Oh dear, no, I've done the wrong thing. That's it. People may know about these Einstein-Podolsky-Rosen type of experiment. This is quantum entanglement, and that got the Nobel Prize just after I did. Quantum entanglement is a real effect, and it's a very strange effect. In this example, time is going up the picture again. I'm considering Alice is taking the left-hand thick line and Bob is taking the right-hand thick line. They move away from each other rapidly, and then they slow down with respect to each other. Initially, they are given a spin 0 particle, which splits into two spin half particles. Alice carries one of them away, not looking at it. Bob carries his along, and they keep each of them in a very insulated box. They're not allowed to look for a while. At a certain point, right up at the point on the top part of the left-hand root, which is Alice's part, she decides to make a measurement on it. She measures it in the direction indicated with the arrow, sloping over to the right-hand side. And she finds the answer, no, you got it wrong. No is the answer. She concludes, therefore, it's spinning the opposite way. Now, according to quantum reality, this effect propagates backwards in time along the past light cone. So you see this light going back in time with the speed of light and hits Bob's world line. And Bob, therefore, has a quantum state of his particle, which is the opposite of Alice's state. And that works, he carries that up. He knows what Alice's should, he doesn't know what either of them are. You see, he can't ask his quantum state, what is your state? That's the whole point. He can choose a direction and he can guess at what the state is. He can choose a direction and he chooses up or down. He doesn't happen to choose the same as Alice. He can't know. Alice can't send him a signal about this. It's too late. That would go within the light cone, not the past light cone. That's classical reality. It goes in the future light cone. Now, Bob makes a measurement. He gets a certain probability of one way or the other, and he finds, yes, he's got it right. This gives Alice a quantum reality that she actually was measuring at the time. So that goes back on the past light cone of Bob and hits Alice's world line and makes her state to be, I think it's the up-down. She gets the down state, I think. Anyway, you can fill out the whole picture with what the quantum reality of the state is. And as far as I can make out, it's completely consistent. The quantum reality is an objective thing for the whole picture. It's just that you can't measure what it is. You can have a go at it. You can guess what you think the state is. You can have a theory which tells you what the state should be, but you don't know what the state is. It's not something you can ask the state what it is. That's the whole point about quantum reality. You can't ask what it is. You can only test. If you make a good guess at what it is, you can test whether that's correct. And this picture seems to give you the right answer. Now, this is the sort of picture I have. It's now at the bottom of the picture. I consider a laser which is emitting a high energy photon, which hits a grain of sand or something like that, a tiny, tiny grain of sand, very, very small one. And this is then, it goes through a beam splitter. So it's half the photon goes one way and half of it goes down, roughly speaking. And the part that hits the thing will move it. And you trace your way up the picture, and you see the space-time gets slightly deformed, and the two locations that it could possibly be in get moved apart, and moved apart, until they get to the point where the state reduction takes place. And in this case, it happens to be the left-hand one. And that makes the classical reality is that continuous space-time, which goes right back to the bifurcation point. And that is the space-time, the robust reality, the classical reality, but it's not really sort of determinable until later on. Okay, well, that's the picture. Now let us think about the Libet experiment. In this experiment, Libet was doing experiment where the person where the brain was open and experiments could be performed on the open brain, but also as a finger could be stimulated by an electrode. And the electrode stimulation is indicated by this at the top of a picture. I think that's considered that the sensation, according to the patient, is almost just a tiny bit, about a 30th of a second after the stimulation took place. So basically simultaneous with it. And there is a fast-moving clock which the patient can look at and decide if it was more or less the sensation of when it happened coincided with what the clock was doing, and then that can be checked with what actually happened. But then there are various curious things you can do. You can stimulate the brain, the part of the cortex, which corresponds to the touching the finger, and it takes a little while before, it takes about half a second before the patient feels it. And the bottom part of the picture is more the puzzling thing, is if you stimulate the brain first, and I think it's really part of the thalamus here, Sears tells me, not as the picture I was indicating, don't worry about that. If you stimulate this part of the thalamus, then the feeling, you can feel it as though the finger, sort of as though the finger had been stimulated about half a second later, but you don't feel the actual stimulation of the finger which happened earlier. So it's as though the feeling had actually not taken place yet. So this is a sort of paradox. How can you have something unfelt which would have been felt had not this brain stimulation taken place about a quarter of a second later. So this is a very puzzling feature. But the argument is that, and according to Stewart, there's a certain part of the brain which is involved in the conscious perceptions. And at that point, it takes a little while for the signal to get up there. And then there would be quantum alternatives. So suppose there's the tennis player who wants to decide whether to hit the ball cross court or down the line. And this decision is made very late. The actions that could be performed to do it one way or the other would be already programmed in superposition. So they'd be already both there. And the choice of which one to make is a quantum superposition choice. And so that this can be made as a classical alternative. It has to be worked out to see whether this could be really made consistent. And you do need to have this retroactive aspect in order to make sense of how this curious feature that one seems to have in these Libet experiments, which have been around for now over 20 years, 25 years or so. So Stuart tells me that it's difficult to perform these experiments now, but it would be very interesting to see if one could still do this kind of experiment and to see whether there is this kind of retroactivity, if there is a superposition of different quantum possibilities, and if the conscious choice of one of those in superposition could then be effectively retroactively done without getting into trouble with causality. That's an absolutely crucial thing. And the quantum reality does not get you into trouble with causality, as I was trying to indicate in the EPR picture I showed you, that there is not a contradiction with quantum reality, with the actual sending of signals. You see, you can't send backwards in time in this way a signal. However, you can affect the quantum reality, and maybe you can do something like perform an act in a table tennis or something like that. That would have to be explored very closely as far as I can see. Thank you very much.
Thank you very much, Roger. Do we have time for one or two questions for the next? Yeah.
Thank you, Roger, for your talk. So I'm wondering, given the history of the question of conservation of energy relating to free will, whether you have a view on if free will is related to vacuum energy or where the energy relating to free will might come from.
Well, I don't quite see the energy question because it's not nearly you can make a decision which uses very little energy. So I'm not quite sure that if the term energy is necessary in this discussion. The question is more to do with free will. And yes, there is a role, certainly a possible role for free will, which has to do with the quantum choices. They if you like, well, in the Orch-OR proposal, the OR part of it is the objective reduction. So that is the quantum state reduction part of it. Now, is there some element of decision of some kind which could be assigned to an element of free will? I'm rather sympathetic towards that idea. It's a bit hard to know quite what free will does. People often say, well, you didn't have this choice. But it's a bit like making the choice about whether to send the ping pong ball to the right or to the left. And okay, am I deciding something there? Well, I'm claiming I am deciding something there. It is in some sense a conscious decision. It's not energy, though. The energy is more like the thing which is the time. Well, you see, energy is conjugate to time. So it has to do with the rapidity with which you make a choice. So I'm not quite sure whether bringing energy in at this stage is helpful. But it is a disturbance of the system, sure, but it's a quantum disturbance of the system. And is that quantum disturbance enough to call it a free will action to decide whether the ball goes to the left or the right? I'd like to think so. And certainly, if there's going to be any room for free will, that's the only place one can see it, as far as I can make out. Go back to Laplace and his ideas that somehow the universe had no choice. about what it does, and that was certainly the implication of Newtonian dynamics. But now you don't have Newtonian dynamics. You have something which goes beyond it and seems to have a role for something that one might certainly identify with the feeling of free will. And what that actually means, one might have to go into a more detailed theory.
I got one over here. Got one over here.
What? Okay, go ahead. Hartman.
Roger, if I understand you correctly, you're proposing that if a system, let's say a qubit, goes into superposition and then an OR event happens, then after that it is as if the system never really went into superposition but only pursued one of the two possible paths. Is that what you're proposing?
Well, that's the classical reality picture, yes. You have to hold them both because quantum reality, I mean, I didn't have enough time to talk about this, but I have a thing which I call the Hemingway paradox. You see, poor old Hemingway shot himself with a shotgun or something, and according to this scheme, his decision to pull the trigger would have been too late to influence, because the action of the gun would have taken place in the classical world before his decision to pull the trigger. But it's not inconsistent, because his decision to do something was part of a quantum world. So it will still be part of quantum reality, but it has been sort of removed from the classical reality picture, the sort of robust classical reality. You have these branches going off, which are, if you like, the three-wheel choices, but it's hard to know. I mean, what do you say? Is there any choice when the classical reality has determined one or the other? Well, hard to say what this means. So, I mean, clearly a good question, but it's, as all questions about free will, it's hard to know what it means. You see, once the choice is made, you could say, well, was there any choice? Because that's the way it came out. Whether it came out half a second later or half a second earlier, it doesn't make that much difference in a sense. What's set in stone is the classical reality. But nevertheless, if you preserve things for a long time, and you could do it, if you have your quantum state preserved very, very, I mean, maybe memory does this in some way. It's quite possible. You can preserve quantum spins in a way which is not disturbed for a long, long time. So it is quite possible. You could have things which are preserved in quantum reality states and only probed later on. Quite possible.
One final question, please, Roger. Anita.
Yeah.
Hi, Roger. This is Anita Goel. Nice to see you again. Einstein argued in the EPR paper that somehow the quantum mechanical description of reality is incomplete. And you have often said that, well, actually, I'm going to ask you, do you feel that in order to understand life and consciousness, we need to radically revise 20th century physics, and there's something missing fundamentally in our understanding of quantum mechanics?
Yes.
And if we understand that, we would somehow reconcile quantum mechanics and general relativity. Could you elaborate on that?
Yes, well, there's separate questions in effect, but I'm regarding them as the same question in a sense. Well, it's part of, see, what people do argue that you've got to bring quantum mechanics and general relativity together. That's quite true. I agree with that. But most of the discussion on that topic is quantizing gravity. So the argument is quantum theory is the theory of the small, if you like, and big things are made out of small things, and therefore it's also a theory of the big if you followed it up. I'm not sure if that's the argument people make. But sort of the view is that you've got to impose quantum mechanics onto general relativity. My view is not that. My view is, in fact, a much more important part of it is general relativity has to solve the riddle, the basic riddle of quantum mechanics, which is how you make sense of state reduction. The collapse of the wave function, I mean, Einstein and Schrodinger and people were much politer than I'm trying to be. They were saying quantum mechanics is incomplete. I'm making a stronger statement. It's actually not even quite correct. For a big object, it doesn't give you the right answer. Because for a big object, the collapse of the wave function will just happen spontaneously by itself, and it will happen so fast that it's just the wrong answer, quantum mechanics. You really need to bring GR together, and that was sort of what I was trying to indicate at the beginning of my talk. When you bring the basic principle of general relativity, which is the principle of equivalence, and try to study that in accordance with the basic principle of quantum mechanics, which is the basic superposition principle, you lead yourself into a contradiction. The principle of equivalence is really very much not consistent really with the principle of superposition. And it leads you to a belief that the superposition becomes unstable over a sufficiently long time. It's a very long time if you have a quantum system where people never notice it. It's a very short time if you have macroscopic bodies. It's a long enough time, as I said, but for systems that have produced time that nobody's seen this effect yet. There's a good reason. Experiments have not yet been able to produce quantum systems isolated enough from the environment that you can isolate out the superposition and see whether the collapse takes place. There are experiments in the pipeline for looking for such effects, but they haven't been achieved as yet. But the fact that gravity comes in is a separate story, which I hinted at in what I said earlier in my talk here. Sorry.
Thank you very much. Before we thank Roger, let me just tell, for Roger's benefit, the next talk will be quite relevant to what you just spoke about. So with that, let's give Roger a great round of applause. Thank you so much.